Oh, hello guys. Alright, so part of this video is a review from last time, and then the other part is actually new content. So let's begin by the review. So the review, we're looking at different states of matter. So I'm going to go over a few things that you should have gone through in your reading. The first thing is the kinetic theory and how we think about gases. That's where we're going to begin. So the kinetic molecular theory says that we consider gases as having a very significant volume, meaning each individual particle has very small volume. We're not talking about the volume of overall the gases. Obviously, it takes a huge volume. But we're talking about individual spheres. You can think of it that way. And one key thing, especially now, is going to be that they don't have intermolecular forces. So the intermolecular forces between them are negligible. And if they're put in a container, they're going to collide against the container, and that collision we call pressure. Okay, so if you think of gases as those spheres, and they have a lot of energy, and they're just colliding against a closed container, every time they collide against the wall of the container, we consider that as a gas pressure. In the periodic table, there's a group of elements that are known in the gas phase, and they're usually nonmetals. Not they're usually nonmetals, they're all nonmetals, as you can see over here. In red are the gases, okay? In red are the liquids, and then everything else is a solid. In terms of gas pressure, pressure has to do, is very related to temperature, okay? And is also related to volume and concentration. Okay, so let's look at individual cases. So when you have a container here, this is a container. The spheres represent the gases. And this is a gas gauge. This is how you measure gas pressure, right? So if you have low temperature, you're very likely to have a low gas pressure. That's because at low temperature, there's less, the molecules are moving less. And if the molecules are moving less, they're colliding against the container less. The second case where you do add heat to the system, so now there is an increase in collision because the molecules are just moving faster, and that's also going to cause the pressure to increase. The other way that we can manipulate pressure is by decreasing the volume. So if we maintain the temperature constant but we decrease the volume, obviously there will be more collisions because the molecules have less space to move around. So that will lead to higher pressure. And then lastly, if you have a container and you keep adding gas to it, the gas are going to start bumping into each other and bumping into the container more often, and that's also going to lead to higher pressure. The other thing that we need to know about the substances that liquids as well as gases, we call them fluids. Fluids are anything that flow. So this is a substance. I'm not sure what substance this is, but this is obviously a liquid. This is iodine and is a gas. Both substances flow. And I actually have a really nice simulation here. Let me just show you this. Okay, so this is water as a solid. Okay, so obviously it does not flow. And then let's do it as a liquid. Okay. And then lastly, let me show you as a gas. You can see they're moving quite fast, right? So that's what makes gases gases, because they move very fast. So let's do this. Okay, they definitely flow, they just don't stay in a container, right? So that's the idea. All right, let's see what else we need to cover. All right, in terms of movement, there is three ways that substances move. The first one is vibration that happens with all substances. Okay, they all vibrate, they're just moving back and forth really quickly. The second one is rotation, they're just rotating around themselves, and that happens with gases and with liquids. And then we have translation. Translation is just when they're moving linearly in a long distance, okay? And this happens with liquids and gases, definitely not with solids. Okay, so showing here, gases, they vibrate, they rotate, they translate. Liquids, they vibrate, they rotate, they do some translation, meaning they can move back and forth, but not very much, because again, they're kind of sticking to each other. And then gases can only vibrate, they can't really move very much because they're stuck in a structure. And actually, I'll show you that right now. Let's just talk about that right now. So let's start with the neon. Okay, so right now this is the temperature right here showing here. And then right now it is a solid, so you can see it's only vibrating. It's not able to move very far, it's just vibrating. If I apply heat to it, I can see that they begin to what we call translate or move a little bit. They can rotate a little bit. You cannot see rotation here, but they start to move. And then eventually they will go from all three types of rotation, all three types of movement, the vibration, the rotation, and the translation. Okay, and let me show you a different one. Let me show you water. So here's water. The one thing for you to notice is that notice that water takes up quite a bit of a volume as a solid. This would be ice. Okay? And then if I apply heat to it, okay, something very special happens. The volume of the water changes, it actually decreases, and that's why ice floats over water. That's because ice is less dense than water. The reason for that is because water has what we call a hydrogen bonding. So when water becomes a liquid, the hydrogen bonding becomes stronger, so it pulls the molecules towards each other closer, so it has a lower volume. But let's make this into a gas. And when I make this into a gas, what I'm doing is I'm breaking the intermolecular forces between those. And I want to show you here, now you can clearly see rotation, right? They're rotating. Okay, so you can see the rotation. So in here, let's start here. In here, internal molecular force is very strong. There's a lot of stickiness. In here, for water is actually more, but then as gases, we assume that there's no intermolecular forces. And since that we're talking about intermolecular forces, and a lot of you in the previous activity were struggling in differentiating between intermolecular forces and intermolecular forces. So the way I like to think of intramolecular forces are bonding, and we did a whole unit on bonding. Intermolecular forces, they're just stickiness, but they're reversible. So say you have a magnet and you want to put in your fridge. If you take a crazy glue or a crazy glue and you put it on a magnet and you put in your fridge, that's going to be permanently attached to the fridge. You can think of that as bonding. However, intermolecular forces is reversible. So if you take the magnet and you just put it on your fridge and you remove it and you put it again and you remove it, it's reversible. So intermolecular force is reversible. It's not bonding. Okay? It's very weak. There are three types of intermolecular forces. This one, let's start with the weakest one, which is London dispersion forces. Those are for non-polar molecules. So non-polar molecules, they kind of stick together, not very much. Okay, so non-polar molecules, they a little bit stick together. When they come close together, this is what happens. So by the way, this is bonding. Okay, and this is just stickiness. Okay, so bonding, kind of stickiness. And they're kind of sticking together because the nucleus of each atom just stores the electrons of the other atoms. Okay, and when that dispersion occurs, there's a little bit of separation of charge, not very much. Those yellow blobs are electrons. There's a little bit of separation of charge, but again, not very much. Okay, but it still occurs. Let's look at something stronger. We call a dipole-dipole. Okay, so the blue and the red is a molecule. Okay, there's a partial charge, so they're definitely polar. Okay? And those little hashed lines, they are intermolecular forces. So the dipole, just two poles, meaning it just means the positive and the negative, they attach to each other. The positive and the negative, they keep attaching to each other. Again, it's just a stickiness. It's not a permanent bond. And then the final one is hydrogen bonding, which is a type of dipole-dipole. It's just way stronger. Even though it's called hydrogen bonding, don't get confused. It's not a full bond. Okay, so this happens with anytime hydrogen bonds to either nitrogen, hydrogen bonds to oxygen, or hydrogen bonds to fluorine. The reason for that is hydrogen is very weak. So you can think of this as major partial charge. This is a major positive partial charge just because hydrogen is so weak. Okay, so you can think of that way. Again, it's just a dipole-dipole, but whoever bonds with hydrogen kind of hit the jackpot just because hydrogen is so weak. So it's so easy to kind of pull its electrons. Okay, so that's the whole idea. So it's called hydrogen bonding. So back into this, okay, let's look at this. So what makes this a solid is the intermolecular forces. In this case of neon or argon that you guys did the model, let's do argon. The case that you guys did the model for argon. What's holding it together as a solid is the intermolecular forces. In this case, just the London dispersion forces. However, when heat is applied, it begins to break those intermolecular forces, okay, and form into a gas, which kind of just start to separate away from each other. And then as a liquid, and then as a gas, there is no stickiness anymore. They're just free. Okay, so you can think about that way. All right, so this is from your reading. Those are the three different types that I talked about before: hydrogen bonding, dipole interactions, and dispersion forces. So that was lesson 1. Then let's go to today's lesson, which is lesson 2, which is phase changes. The modeling part is going to be lesson 3, so when I see you either Thursday or Friday. But today I just want to introduce you the concept, so when I see you next, I'm going to actually have you model this. So again, should be a review from 8th grade. A transition between a solid and a liquid. If it's going this way, from solid to liquid is melting. If you're going from liquid to solid, is freezing. If a liquid goes into a gas, we call it vaporization. If a gas goes into a liquid, we call it condensation. Usually this is how the direction that it goes, from solid to liquid to gas. There are cases, it's rare, but there are cases where a solid goes straight into a gas, or a gas goes straight into a solid. So when a solid goes into a gas, we call sublimation, and when a gas goes into a solid, we call deposition. Okay? The energy of the system increases as you move this way. So as you increase, so say you have a solid, and as you increase the energy, you move into a liquid. As you increase the energy, goes into a gas. And you saw that in a previous animation that I did, where you can see that gas is moving way faster. Right? So this is a phase change diagram. All right, so this is pretty important, so I'm going to kind of walk you through slowly. So this is a phase change for a water molecule. So say you have water into a container, and I apply heat to it. So as I apply heat to the water molecules begins to move faster and faster and faster and faster. And then it's going to reach one point, this point right here, which is the melting point. By the way, this is ice. I'm sorry. This was ice. And the ice is vibrating faster and faster and faster and faster. And it's going to reach a point what we call a melting point, where all this energy that I'm going to keep adding to the system. Again, I'm heating it up. I'm still heating, but the temperature will not change. All this heat is going to be used to start breaking those intermolecular forces. Those intermolecular forces are going to start to break. Okay, and I'm going to keep adding heat until most of them are broken. And then once all of them are broken and they're all free, then temperature is going to start increasing again as the gas particles begins to move faster and faster and faster. So let's look at an animation of this. Where is it? This is it. All right, so this is a solid. Let me just walk you through. This is a solid. Right stage, I wanted to a gas. Okay, this is the graph that I just walked you through. So this is temperature, and this is heat, and the heat is being applied by this stove. Okay, and again, this is temperature. This is the energy applied by the stove. This is the temperature of the substance right now. So let's do this. So as you can see, I just want to walk you through so you can see it. So you can see it's a solid and it's increasing in temperature. Okay, so right now the temperature is being used to convert from solid to a liquid. So all this energy is being used into melting. Okay, when that phase has been reached, the energy begins to go into increasing movement, so a higher temperature. So you can see the temperature is increasing again. Okay, so all this energy is going into making the molecules move faster. You're almost getting there. Okay, let's pause for a moment. What do you guys think this is going to represent? Okay, so what do you think this is going to represent? Hope you guessed it right. This is the vaporization part. That's when the molecules are going to go from a gas or from a liquid into a gas. So again, no increase in temperature. Look, the temperature is constant. It's just causing the molecules to go into a vapor. And as you may guess, the vapor particles now, obviously the stove does not make sense at this point, but pretend that the stove is still acting on the gas particles, is causing the gas particles to increase movement, so there is increase in temperature. Okay, so that is the idea behind. All right, so I mentioned this before. Boiling is when the intermolecular forces are being broken between a liquid, okay, between liquid. That's what we call a boiling. Okay, so that is the sticky part where we're talking about vapor. So liquid goes into a gas phase not only when it's boiling. For example, if you take a glass of water, which obviously is not boiling, just a tap water, and you leave it outside for a few days, you're gonna notice that a lot of the water is gonna disappear. That's because it goes into a vapor. Okay, so it's not necessarily needing to be boiling in order to go into a vapor. There will be a little bit of liquid that's able to escape even before it reaches the boiling point. And we call this vapor. And obviously, because it's a gas, it has pressure. So we call this vapor pressure. Different substances have different vapor pressures. Vapor pressure, things that goes into gas substances that goes into gas very quickly, we call them volatile. And I mentioned this to you before. But let's look at how vapor pressure affects boiling. So say you have something at sea level, okay, you have a liquid at sea level, and right now there's an amount of pressure being applied to that liquid. Okay. And say this is a 70 Celsius, so it's below boiling point. So the pressure applying by the atmosphere is greater than the pressure applied by the liquid. Okay, so the liquid stays in a container. However, when you increase the temperature to a boiling point, which in the case of water is 100, the pressure applied by the liquid equals the pressure applied by the atmospheric pressure, or the pressure applied by the gases in the atmosphere. Those two are equal. Therefore, the liquid particles are able to escape, right? And that's when we say it's boiling. However, if we take this container, and we take this container all the way up a mountain. So on a mountain, obviously there's less pressure being applied on us just because we moved up, so there's less air on top of us, so there's less pressure. Because there is less pressure, the pressure applied by the water can easily overcome the vapor pressure, or the atmospheric pressure. So that causes a liquid to go into a gas much quicker. So up in high altitudes, water can boil way below its normal boiling point. Okay, so in the case of here, Mount Everest, water can boil at 70 Celsius. I don't know if this is accurate or not, but this is where this is analogy is going. So the higher you go, the less pressure there is into pressing against the fluid, the easier it is to go into a boiling. Okay, the other point I like to make, and this is about solids, when heat is added to a solid, to go from a solid to a liquid, what you see here is that the molecules are able to pass by each other, to start moving against each other, and you see that there is less order into the system. Okay, and this is an ionic. For ionic and metallic bonding, in order for it to go into a different state, you actually have to break the bond. For molecular particles, you break the intermolecular forces, which is easy. For ionic bonding, you actually have to break the bond itself. And I don't know if you remember, but you actually did a research of why was it so hard to melt ionic compounds. I think it was like 900 Fahrenheit, some crazy number, but that's because you actually have to break this really strong force here. All right, and this is my last slide. This is called a phase diagram. So each substance has a phase diagram. It doesn't say, yeah, this is the phase diagram for water. So each molecule will have its own phase diagram. So this is how you should read it. So in here, I pointed out to you that pressure plays a huge role on what state of matter something is. For example, if I have water at 70 Celsius here, most of it will be a liquid. But if I'm on top of Everest and it's 70 Celsius, my water, most of it will be a gas. So pressure plays a huge role on the state of matter. So it's going to be a graph of pressure versus temperature. Okay. The different sections here represents the different states. So right here is a solid, right here is a liquid, right here is a gas. The line here, so between solid and a liquid, this is going to be the melting point line. Between a liquid and a gas, this is going to be your boiling point line. And between a solid and a gas, this is your sublimation point line. Okay. So at 1 atmospheric pressure, which is at sea level, so standard pressure, at sea level, so standard pressure, water boils, or water melts at 0 Celsius. So this is how you read this graph. Water melts at 0 Celsius and it boils at 100 Celsius. Okay, because this is where the transition is. There are a couple important points I also wanted to bring it up. This place where all the 3 lines meet is called a triple point. And this is a point where under the right pressure and the right temperature, the 3 phases can exist. So you can have a solid, a liquid, and a gas. And then there's actually, if you go above this line here, it's called a critical point. That's when phases stop being distinguished. So a liquid, a solid, and gas, they stop looking exactly how they are. they lose a lot of the properties, what makes a liquid, what makes a gas, and they start blending together. And this is actually very useful. Um, do I have it here? Oh, I removed it. So people use supercritical fluids, or we call it above critical point, to do all sorts of things. For example, to decaffeinate coffees and teas, for a green alternative to dry cleaning. There were so many applications, I forgot of some of them, but some the applications are quite useful. We call them supercritical in most cases of fluids, but it's just when the phase diagram stops, and there's actually stopped the very well definition between a liquid and a gas, or a gas and a solid. Okay, so you're aware of that. So that is the end of it. Please let me know if you have any questions. Bye bye.